So welcome back to the lecture series on metric space and topology, and let us begin with a very important topic that is called compactness. Okay, so this compactness is very useful to give the notion of some finite properties related to topological spaces. Okay, so for that we need to know something called what is an open cover for a topological space. Suppose X be a topological space. So let us consider U be the collection of certain open sets. Let's say UI. This collection may be finite, maybe infinite, maybe countable, maybe uncountable, whatever. So this collection is said to be an open cover for the topological space X if the entire union of all these open sets is basically capital X. Okay, that means suppose we have a topological space, right, like this, one topological space, and I can have this kind of open sets like this. Okay, so each are basically UIs. Each are UIs. These are all UIs. Okay, and what is a subcover? Subcover means suppose X comma tau is a topological space, and let us consider that this U is an open cover of X. And what is subcover? Subcover means certain U1 is a subset of U, and set of all open sets G belongs to U1, G is itself X. So that means once you have certain open sets, so you need not to take all the open sets from this open cover U. It is enough to take certain number, I mean maybe countable or maybe uncountable, whatever. It is enough to take a subset of this open cover, and you can consider that the entire U1, this itself acts like an open cover for X. Okay, it is an open cover. That's why it is a subcover. So then E1 is said to be subcover of U. Okay. Now, what is a compactness? So, what is basically notion of compactness? If we say that this particular space is compact, that means, of course, I mean, suppose you have a room and we say that it is a compact, means there are sufficient amount of people or sufficient amount of entities are there, and there is no space to put another more entity or more person, right? So that basically means that it is compact. So similarly here as well. So suppose we consider X as a topological space, and we say that this is compact if for any open cover it has a finite subcover. That's why you have in the beginning I told you that compactness basically introduces the notion of finiteness at certain stage. Finite subcover. Okay. So as is a finite subcover means suppose that means let this entire collection UI small I belongs to capital I. This is an open cover. Then of course there exists certain small natural numbers such that certain U1, U2 up to UN. This, let us call this collection to be as U, this belongs to U, such that this union is itself X. Okay. So this is basically notion of finiteness. Let us consider a very simple example. So suppose we have any finite set, most trivial, any finite set with discrete topology. Okay, so as it is a finite set, so of course in fact if we take any open cover, let's say x1 up to xn. Okay, so if I take any open set or any open cover for this topological space under the discrete topology, that means basically that open cover itself is finite, right? That means it will itself a finite subcover of that. So that means it is by default this is compact, right? Because since the space or then the underlying set is itself finite, hence this set must hence any open cover must be finite. Okay, so it is compact by default. Some more another kind of example. Suppose we take R associate with cofinite topology. Cofinite topology. Okay, so that means suppose we consider any open cover. Let's say ui, small I belongs to capital I. This is an open cover. So that means if I take at one ui, let's say some ui i1, so ui1 complement, this is finite, right? So ui1 complement, this must be of the form x1 x2 up to xn. Now where this xi belongs to, xj belongs to, that means xj belongs to capital X. So that means there exists some small j belongs to, or let's say not xj, so for each xj there exists some uj belongs to, let's say this u, says that xj belongs to uj. Okay, so that means first you take one u1 i1 complement any open set, then you consider x to be as ui1. So ui1 takes all the elements other than this capital x1 to xn, right? Then you take union with entire union of j equals 1 to n uj. So ultimately it is finite. All right, so the finite subcover which is getting associated over there is basically ui1 u1 so on up to un. This is a finite subcover. Okay, this works a finite subcover. All right, okay, so these are some beautiful examples of compact topological spaces. So in later cases we will see some more beautiful example. In of course we will be happy if we could find some example of compact topological space or some criteria, some basic or let's say some suitable version of compact topological spaces in normal Euclidean topology where we are familiar to work with. So we'll be happy. So yes, of course we'll find those kind of things later cases. All right, so let's move ahead. So there's a theorem that says that suppose X is a compact topological space and let's say Y is subset of X, this is closed. Okay, so then Y must be compact. Okay, so let's consider, so Y is closed means Y complement is open in X. Okay, so let's consider that just keep in mind this one. So let's consider that any union of all small I belongs to capital I, Gi, this is itself I. So what is Gi? So Gi, this is open in Y. So each Gi must have the following form, that is OI intersection with. So each OI is open in X. Okay. Now as Y complement is open in X, so I can consider I belongs to capital I, Gi union with Y complement union with, so that means it is same as U union with Y union with Y complement. So it is basically same as X. So that means I get an open cover B, which is basically each Gi and singleton Y complement. So this collection, just you adjoint Y complement in the collection, and then thus we can cook up a prompt open cover. So that means as X is a compact topological space, so B must have finite subcover. So that means let's say the finite subcover, let's consider this as B1. So this now this B1, this have some finite subcover. So this finite subcover may include Y complement or may not include Y complement, or may just be considered of certain GIs. Okay, so let us consider that B1 includes Y complement. So that means you can write union of small I equals 1 to n Gi and union with Y complement is X. So as these elements are coming from open cover of Y, and of course if we consider this one basically same as Y, because if we take any small x belongs to X and if it is in Y, so of course it is not in Y complement. That means it has to be inside this union, right? That means it has to be inside this GIs. That means this entire collection of GI is basically same as Y. So that means this is Y. So this collection, that Gi small I equals 1 to n, this associate the finite subcover. Finite subcover. But if we consider, let's say, union of all small I equals to 1 to n Gi, this is not the same as X. So of course then this has to be in Y, because this collection, this is subset of Y, but Y is closed subset of X, so it has to be there. So that means you can easily consider that, we can easily say that Y complement must have to be in X, because we know that X and Y should not be same together if we just have it. So of course Y complement must be there, right? Because by intuition you can consider that X is larger topological set than Y. Alright, so this is how one can define. So for any of the cases, Gi is acts as a finite subcover. Okay. Alright. So that means we get Y is compact topological space. Alright. In fact, not only the compact topological spaces, but also under the continuous function of compact space also compact. That means theorem says that suppose f is a function from x to y is a mapping, a continuous mapping from topological spaces, whereas x is compact, then fx is compact in y. Okay, so it is also very easy to prove, there is nothing challenging. So let us consider that this gi, small I belongs to capital I, is an open cover for fx. So each gi must be of the form uy intersection with fx. Okay, for each uy. Now, okay, so these uys, this must be open in y. So now if we consider that, let's say consider a collection B which is consisted of all the open sets f inverse uy. So these are open in x. So now can you find that union of all small I belongs to capital I f inverse uy? So if you take any small x belongs to this one, so that means fx must belongs to 1 of the uy1. Okay, so that means, and of course this belongs to f of x, so that means fx, this must belongs to gi1. Okay, so that means this exactly gives the open cover. So we get union of all small I belongs to capital I f inverse uy is itself x. Now x is compact topological space. We have, that means this collection is of course an open cover for x. So that means hence we must have a finite subcover. Okay, so as it is a finite subcover, that means we can write x to be as union of all small I belongs to capital I f inverse, sorry, not entire I, rather to take some finite number of open sets u by's. So then we can show that this capital F of so of course we take capital F of x, this is union of all small I belongs to equals 1 to n fx intersection uy. So that means these are basically gi's. So some finitely many gi's are there. Okay, so that means fx is compact. Okay, now how to characterize the compact spaces, or let's say in terms of the intersections. Okay, so there's a theorem that basically says that suppose we consider x comma tau is a compact topological spaces, so then not right now we should not write it as compact, is a topological space itself, then the finite, then the following equivalent. It's a very equivalent criteria for compactness of topological space in terms of intersection properties. So first of all is that x is compact, and number 2 is let's say ui, small I belongs to capital I, ui, these are closed sets. Okay, not ui, because we have denoted the open set ui, so let's go ci's. These are closed sets. These are closed sets such that intersection of all small I belongs to capital I, ci is empty, so there exists in belongs to natural number such that intersection of all I equals 1 to n ci, this is empty. That means any finite any collection of closed sets with empty intersection has a finite subcollection that also has a finite empty intersection. So basically this is another version of compactness via the closed by the in terms of closed sets, right? So it is basically nothing to prove. So it is, we have said that X is compact means any open cover is finite subcover, right? Suppose X is compact, and let us consider any collection of closed subsets having this particular property. So that means what this particular property says. So this particular property basically implies that union of small I belongs to capital I, ci complement itself X. So that means this particular union is based ci complements, collection of all ci complements. This serves as a open cover for X. So that means as X is compact, we have assumed, so it must be compact. So I mean it must have finite subcover. Okay. So as it is a finite subcover, so that means there exists small natural number such that in union of I equals 1 to n ci complement, this is X. So that means intersection of small I equals 1 to n ci, this is phi. Alright, and converse statement itself, that suppose we take converse, also very easy. So converse, let collection small capital I, this is a open cover, we can name it as a closed cover. I don't know how to name it, but let us name it a closed cover. This is our own notation. Okay, yeah. So consider open cover. So union of all small I belongs to capital I, ui is basically same as X. So that means intersection small I belongs to capital I, ui complement, this is actually phi. Okay, because intersection of all open sets has to be, if I take the complement of the union, it has to be intersection by the closed sets. Now ui is open set, so I complement, this has to be closed. These are closed, right? So this is a collection with empty intersection. That means it must have a finitely many closed sets of this form, which is also finite empty intersection. So that means we can write small I equals 1 to n certain ui complement, it is phi. So union of all small I equals 1 to n ui, this is X. Okay, so it is a finite subcover. Okay, so this is how one can define the compact compact definition of compactness by the closed sets, because open set and closed sets are basically both sides of a particular coin via the I mean there is a connection. Basically connection is made via the complement, right? If you take a closed set and give the complement of that closed set, you will get an open set, and vice versa. So both are basically both sides of a particular coin. All right. So now every time we may not be able to find a finite subcover for in general open sets, right? Because there might be some topological spaces where the open sets may not be easy to visualize, whereas other than the basic open sets. Okay, so that's why we may be concerned about what is the picture in terms of the basic open sets. If we get the same analogous statement in case of basic open sets, then you'll be happy, right? So that's why it's a useful theorem. Study the hash. So this says that if X is compact if and only for any basic open cover has a finite subcover. So what is the theorem statement first of all? So this says that suppose X comma tau is a compact topological space, is a topological space, then the following are equivalent. First of all is X is compact. Number 2, every open cover consisted of basic open sets must have a finite subcover. So this open cover consisted of basic open sets. This open cover consider basic open sets these are basically said to be basic open cover. Okay, means every basic open cover is a finite subcover. Alright, so how to prove it? So one side is very clear, right? Because if we consider that it's a compact topological space, then it must, if we consider any open cover, because when the definition of open compactness, we didn't define any criteria on the open sets, right? Because it need not be basic or something like that. So that's why it is true for any open cover. So that means if it is a basic open cover, it must have finite subcover. So forward direction is trivial. So that means forward is trivial. So what about the backward direction? So suppose we consider a basic open cover. So union of all small I belongs to capital I, Bi, it is X. So these are basic open covers. Basic open sets. Now, be any open sets, because we have assumed that any basic open cover has a finite subcover. So from this we have to construct a basic open cover. Okay, now every Bi is the union of all small j belongs to Ji Bij. So where each Bij, these are basic open sets. So this entire union, small I belongs to capital I, Bi is nothing but small I belongs to capital I, union with small j belongs to Ji Bij. Okay, so these are basically union of basic open, and this is itself capital X. So that's how we have got a basic open cover. So what is the basic open cover? So basic open cover is of this form: small I belongs to capital I, B I J, where j belongs to small j, capital small I. So this is a basic open cover. So as this is a basic open cover, so it must have finite subcover, right? So X must have finite subcover means there are some finitely many subcovers. So let's say BI1 J1 union up to BIN Jn is X. Okay. Now each BI1 J1, now BI1 J1, this is inside BI1, BI2 J2, this was inside BI2, and thus BIN J, this was inside BIN. Okay, so this entire union of all these open set, this must be inside entire union of all these open sets. So that means basically this entire union is basically X, right? Because you have got it here. So that means union, this entire union is basically consisted inside BI1 union up to BIN, right? That means X basically same as BI1 union up to BN, because all these BIJs are inside X, so their entire union has to be inside X, right? Because open sets cannot be larger than main topological space, so it is basically BIN. So this is how one can construct a subcover. So what do you mean subcover? So subcover is basically BI J equals 1 to n. This is the subcover that will work. Okay. So that means to define that whether or to show that whether a topological space is compact or not, it is enough to work with the basic open covers. Okay. So that's this is a very short introduction of compact topological spaces, but in the latter cases we will have, it is a very short tool, but this is very useful to show that whether a constant continuous function is basically existing between the topological spaces or not, or something other properties. Okay, so in the last we will just stop it here, but just having a very short but important theorem. In the last class we have discussed something called product of topological spaces. Now we have shown that under the continuous function the compactness preserves. So one can of course get be interested to know that whether under the product it is remain constant or not. So there is something called tychonofs theorem. I maybe have some mistake with the spelling. Yeah. So what is the tychonofs theorem? So tychonofs theorem says that suppose we have this collection of xi's. These are compact topological spaces. Then the product of these compact topological spaces is has to be compact. Okay. So it is quite easy to prove. There is nothing to prove. We will just prove it via something called intersection property. So what is the finite intersection property? So the finite intersection property says that suppose we consider an arbitrary class of sets, let's say AI, these are arbitrary class of sets. This collection is said to have a finite intersection if for any small n belongs to natural number a1 intersection a2, any finitely many AIs if I choose, the collection has to be infinite and has to be non-empty. Okay, so whatever finitely many sets I choose from this collection, their intersection must be non-empty. Okay, because that means they will intersect at a certain stage. So that is very important. And okay, but what is the relation between this finite instance property with the compact topological spaces? So let us see. Suppose there is a theorem. It is basically hidden in this above criteria. Okay. So what does it say? That suppose if you have exit compact topological spaces, then every here. So here. So if exists compact topological spaces, if and only if any arbitrary class of open sets such that this has empty intersection, okay, then this must have a finite number of closed sets which has empty intersection. So these relation between the finite intersection property and compactness compact topological space is hidden inside there. So let me just precisely write it here, that suppose X is compact topological spaces if and only if any arbitrary class of closed sets with finite intersection property has non-empty intersection. So it is basically a contrapositive statement of that. So that means suppose you consider any arbitrary class of closed subsets Ci such that for any finitely many open closed sets C1 up to Cn, this entire is non-empty. For any n belongs to natural number, this is true, right? So that means by contrapositive statement of this particular form, if we apply the contrapositive statement, that means it says there if we have this one, then there exists certain like this. But we have assumed that we consider this one so that this is true. That means this entire intersection this has to be true, has to be non-empty, right? So that means this entire intersection has to be non-empty. So okay, let us assume that we have certain closed subsets and this entity small I belongs to capital I, Ci, this has to be non-empty. Is contrapositive. But what about this converse statement? Converse is also very easy. That suppose we consider for any open subset this is true, okay, so then we consider any arbitrary closed subsets such that this entire union small I belongs to capital I, Ci is phi. It has empty intersection. So that means so that now assume that for any property, for any natural number, if we take any finitely many open closed sets, this is phi. For any C1 intersection to Cn, this is phi. Okay. So as it is phi, so that means this entire intersection has to be non-empty. But if I assume that this is empty, so that means there is a contradiction. That means there is a certain n natural number so that this is true. So it doesn't have any finite intersection property. Okay. So that's why once you want to work with certain topological certain collection of closed sets, and to prove that any topological space is compact, so make sure that the collection of closed sets that you have chosen doesn't satisfy the infinite intersection property. Okay, that's the key idea to prove that tychonofs theorem. Of course, one may have different approaches, but this is the most shortest strategy that I have found. All right, so to prove okay, let us change this page. to prove the Tychonofs theorem, so let us consider any non-empty class of closed sets. Let's say if J that has a finite property, small j belongs to capital J, these are closed in, let's say, product of xi's. Okay, so which is a closed subsets, then of course is fj, this must have the product of fij where fij, this is xi if I is not equal to j, and it is fij, this is closed in xj if I equals j. Okay, now so this is how one can find that by the closed open set that we have defined in our cases is basically we give that each closed set looks like this. Okay, now for any, let's say for any I1, let's say I1 belongs to capital I, any element. Okay, now you just fix this previous notion that small I and consider this collection if I1j is a class of closed subsets. Okay, and remember that this particular collection has the finite intersection property. That means each of fi1j's, this also has a finite intersection property. This collection also finite intersection property, because if we take any element is intersection of this, of course it has to be there, right? I mean, if you take any element in this, it of course has to be in this intersection. Okay, so that's why if it has finite intersection property, that means it has also finite intersection property. So that means now each, what is if f1ij's, fi1j's, so each fi1j's are basically closed in xi1 and xi1, so these are closed in xi1, and each xi1 is closed in x. Okay, let I should not take I1 because II is basically not, so it is enough to take I is not equal to j here. Okay, and for any of the cases fi1j is closed in xi. Okay, so yeah, it is it should not write like this. Yeah, fij is closed in xi, yes. Okay, each fi is closed in xi. So xi1 is closed in xi1 is compact. Okay, is compact. So fi1j has finite intersection property. Okay, so that means, so there exists certain small xi1 which is inside intersection of all small j belongs to capital J fi1j. Okay, so that's why we can say that for each I we can do such things and then take xi small I belongs to capital A. This entire product of is an element or tuple from this entire product of logical spaces. This has to be inside intersection of all small j capital J fij fj. Okay, so this is how one can construct so that it has also finite intersection property. But also there is another approach that of course one have immediately figured it out, that via the basic open cover. So suppose we consider x1 cross up to, okay, whatever product we may choose, x size. So let us consider a basic open cover of this form, that small I belongs to capital I, which is let's say small j belongs to capital J. It is, otherwise it will complicate with the notion. So G product of, let's say, small I belongs to capital I, Gij. Okay, so each Gij are open in Xj. Okay, so this is basically, so these are the basic open cover. It is same as, let's say, product. So these are basically basic open cover. So now if we fixed one xi, let's say, yeah, open in xi, yeah, it is xi. So if we fix one xi, so small j, so union of all small j belongs to capital J, gi1j, this is open cover of xi1. Okay, so that means this must have finite subcover. So it must have finite subcover means there exists j1 equals, let's say, gi1 u1 up to gi1 nj ni1, this is xi1. So similarly for every I can get that kind of things. Okay, so then I can choose thus for each xn's I can get, or for each xi I can get this kind of finiteness, and then I can glue or make them together with like this, and I'll get the finite intersection property, finite collection like that. Okay, so this can be another approach for this proof. All right, so this is a very short introduction of compact topological spaces. In the next class we'll start with compactness related to metric spaces itself. Okay, so let's stop it here, and I believe that you will revisit all the previous steps again, and in the next lecture we'll start with compactness in metric spaces and Lebesgue measure, something like that. All right, okay, thank you very much for your patience. Bye.